number 5. Now, when we do problems like this, we always like to underline the information. So let's do that. A 0.15 kilogram ball M with a speed of VI. It is hit straight back at the picture at 22. That would be VF. What is the impulse? Well, I was told that impulse, okay, it's just the force and the contact time. But then I say, wait a second, I can't do anything with that. Because I was given, yeah, but I do know that Ft also equals m delta V. So this is the fit. Okay, so I could do that. J equals, I can build that equation, m delta V. Now this has got a little twist to it. The mass is 0.15 kg. That's easy. But now the V delta V is Vf minus Vi. Let's write a little note to self. That's always the final minus. Now there's a little twist to this problem. I know the initial is 20 meters per second, but I got to be real careful with the final because I might think the final is 22, but it really is not. Yes, 0. Yes, negative 22. That's what makes this a little bit of a tough problem. Now, on what basis is she right? What do you say, Miss Doyle? That was pretty good. She said it was negative 22. Why the negative? Yeah, it went in a different direction. Let's circle this. Hit straight back. So if you're going to call the 20 positive, you have to call the 22 negative. See that? That's an interesting problem. After that, it's a piece of cake. We just multiply, just take that change. That's a really big change. That's like a negative 42 change. That's a negative 42 change. And then multiply. Why don't you do that? I'll pull out the answer. And let's see, what do we get when we multiply? Impulse. Force and contact time. Yeah, Haley? 2 significant digits? Well, let's make it negative 17,000 because we want to keep it. Wait a second. I think I'm looking at the wrong thing. I'm sorry. Yeah, I took it. Totally looking at the wrong thing. It's negative 6.3 kilogram meters per second. Sorry about that. Negative 6.3. Now, where did I get kilogram meters per second? Because I had kilograms over here and meters per second over here. I was looking at totally wrong. So it's negative 6.3, 2 significant digits, kilogram meters. Yeah, that's fine too. But look, this is what I used. I might as well just be consistent with what I use. So you can certainly use Newton seconds because if J equals F times T, it also equals Newton times. All right, this is not, you never get anything like we just learned. If you didn't get a homework on it, it's not on the test. All right, so what is the average force? That's F. Exerted on the bat, on the ball, if the two are in contact for, there's a T. Hey, wait a second. We know the J, and we know that J equals Ft. So can't we just use this? So the F is, so then the F is unknown, but the T is not, because it's 2 times 10 to the negative. I opened up the Microsoft. Why don't you keep working, girls, and I must have hit the wrong thing. All right, once again, J equals Ft. And we found that J equals negative 6 kilograms per second. And we don't know the F. We do know the T. It's really small time, seconds. And so this is pretty simple. We divide both sides by that number using, we get negative 3.2 third. All good? So of course a negative, the bad exerts a negative. Unless you need to show significant digits. So all good, girls? Yeah. Yeah. Say it again. All good? All right, now this one's a pretty tough one. Olympic diver drops from rest. Let's read and underline. So we got her mass. So do this with me. Do this with me. Drops from rest. Or diving board, that's my DY. She hits water and comes to rest after reaching the water. What is the net force of the water on the diver if she's brought to rest in the water? This is actually a 2-part problem. You could say, well, you could say right away, oh, I know what to do. They talked about F and T and M. Okay, this is what they talked about. What do I got? What do I want? And what fits? So naturally, I would use this. But we have a problem. We can't use this formula until we know how fast was she going when she hit the water. Let's write that down. Need to find velocity of diver when he hits the water. And then I could use this. The force of the water, the time that the force acts, the mass of the person, the change of V. So I have to actually do a whole separate problem. Yeah. Perfect. You are so far ahead of us. Let's get there. Good. That's actually exactly what you do. Now let's see where Susanna came to that. Well, Susanna said, you know what? She started from rest. She's on the earth, right? She she went down a distance of 3 meters that was given. And she said, well, then I'll be able to find out how fast she hit the water. And then she looked at all these letters and she said, what do you got? What do you want? What fits? Well, you've got VI, VF, A, and D. And so, Susanna, you are fast. Susanna looked and realized the equation that fits this perfectly, that'll give us the velocity that she hits the water is there. So VF squared is actually unknown. We don't know that. The VI is 0. It's the Earth. We're going to use 10, positive 10. It's not a lab. And 3 meters, you're like way ahead of us. And what did you, so work that out? What does that turn out to see? Does it turn out to be 7.7? Oh, maybe I went 3 significant digits. I think if it goes 3, because everything is in 3, I think, check that again, yeah? Well, that's when she gets into she hits the water takes her to rest. So we've got to find out, we can't do that second part until we know how fast was she going when she hit the water and then the water stopped. You know, yeah. So we've got to do a whole problem before we do the problem about her being stopped by the water. And did you get 7.7? Is that what around? Okay, 7.75. Okay. So the velocity she hits the water is 7. You know what? I probably calculated this. Maybe who knows? So 7.75. Let's get rid of this. So now we actually have to solve the problem. The water stopped there. There was an interaction between the diver and the water. Why did I pick this? Well, it's red. So now we have to do now we actually do the problem because now we know how fast she was. So Ft equals m delta v. Why did I use that? Well, because they mentioned all of these things. So the force is what we don't know, right? That's unknown, the net force. The time we are given is 0.550 seconds. The mass is 82.0 kg. And the final velocity, that's just 0. What has stopped her? And 7.75, you said, meters per second. Of course, this is going to create a negative change of velocity, and therefore a negative force. No surprise, negative force. Now it's a math problem. Just multiply those two and divide by 0.550, and we got the force. And we'll answer in 3 significant digits. Okay, what did you get? Go ahead, tell us. 1160, yeah, 7.75, yeah, I think you get 1160. Oh, okay. So it's actually negative too. It's a negative force. Yeah, go ahead, tell us, Chloe. It's always VF was the final. The final was 0, because the water brought her to rest. Okay. Oops, I left my units out. What's that? Is 0. The water stopped her. She hits the water 7.75, and then water, like you've taken a dive into water. Eventually, the water stopped you. It applies a force to you. Oh, we're not fine. VF. We're told that the water stopped her. VF is 0, and we calculated that she hits the water at 7.75. Right? That earlier work we did, right? 7.75. So, we'll find F. This is what we want to find. Yeah, we're trying to find F, and if we could not find F unless we know both we knew that the final was 0, but we didn't know what the initial was. We had to find the initial. How fast was she going to hit that water? So that's quite a problem, right? You did not like that one, did you? What? Yes, what we found is the initial velocity. How fast was she going when she hit the water? Why did we do that? Because when I looked at this equation, I cannot find the delta V unless I know how fast was she going when she hit that water. So we're going to skip the last question.